The Madelung constant is used in determining the electrostatic potential of a single ion in a crystal by approximating the ions by point charges. It is named after Erwin Madelung, a German physicist, because the anions and cations in an ionic solid are attracting each other by virtue of their opposing charges. Separating the ions requires a certain amount of energy. This energy must be given to the system in order to break the anion-cation bonds. The energy required to break these bonds for 1 mole of an ionic solid under standard conditions is the lattice energy. Formal expression. The Madelung constant shall allow for the calculation of the electric potential via all ions of the lattice felt by the ion at position ρ, where Rij equals Rj is the distance between the Ith and the Jth ion. In addition, Zj equals number of charges of the Jth ion equals 1.6022 times 10⁻19 c4 pi epsilon 0 equals 1.112 times 10⁻10 c squared. If the distances Rij are normalized to the nearest neighbor distance R0, the potential may be written with being the Madelung constant of the Ith ion. The electrostatic energy of the ion at site then is the product of its charge with the potential acting at its site. There occur as many Madelung constants in a crystal structure as ions occupy different lattice sites. For example, for the ionic crystal NaCl, there arise two Madelung constants, one for Na and another for Cl. Since both ions, however, occupy lattice sites of the same symmetry, they both are of the same magnitude and differ only by sign. The electrical charge of the Na plus and Cl minus ion are assumed to be one-fold positive and negative, respectively, and the nearest neighbor distance amounts to half the lattice parameter of the cubic unit cell, and the Madelung constants become the prime indicates that the term is to be left out. Since this sum is conditionally convergent, it is not suitable as definition of Madelung's constant unless the order of summation is also specified. There are two obvious methods of summing this series, by expanding cubes or expanding spheres. The latter, though devoid of a meaningful physical interpretation, is rather popular because of its simplicity. Thus, the following expansion is often found in the literature. However, this is wrong as this series diverges, as was shown by Emersleben in 1951. The summation over expanding cubes converges to the correct value. An unambiguous mathematical definition is given by Borwein, and Taylor by means of analytic continuation of an absolutely convergent series. There are many practical methods for calculating Madelung's constant using either direct summation or integral transforms, which are used in the abled method. Generalization. It is assumed for the calculation of Madelung constants that an ion's charge density may be approximated by a point charge. This is allowed if the electron distribution of the ion is spherically symmetric. In particular cases, however, when the ions reside on lattice site of certain crystallographic point groups, the inclusion of higher-order moments, i.e., multipole moments of the charge density, might be required. It is shown by electrostatics that the interaction between two-point charges only accounts for the first term of a general Taylor series describing the interaction between two charge distributions of arbitrary shape. Accordingly, the Madelung constant only represents the monopole term. The electrostatic interaction model of ions in solids has thus been extended to a point multipole concept that also includes higher multipole moments, like dipoles, quadrupoles, etc. These concepts require the determination of higher-order Madelung constants, also called electrostatic lattice constants. In the case, instead of the nearest neighbor distance, another standard length like the cube root of the unit cell volume is appropriately used for purposes of normalization. For instance, the Madelung constant then reads the proper calculation of electrostatic lattice constants has to consider the crystallographic point groups of ionic lattice sites. For instance, dipole moments may only arise on polar lattice sites. exhibiting a C1, C1H, Cn or Cnv site symmetry. These second-order Madelung constants turned out to have significant effects on the lattice energy and other physical properties of heteropolar crystals. Application to organic salts. The Madelung constant is also a useful quantity in describing the lattice energy of organic salts. Izgorodina and co-workers have described a generalized method of calculating the Madelung constant for any crystal structure.